Imagine an animal alive today that was born before the United States existed, before Newton published his laws of motion. This isn't science fiction, it is the Greenland shark, a vertebrate that can live for more than 400 years, possibly even reaching 500. This creature navigates the frigid, dark waters of the North Atlantic and Arctic Oceans, a living relic from a different era of human history. To put that into perspective, an individual swimming today might have been a juvenile when the Industrial Revolution began. Its entire life unfolds on a timescale that is difficult for us to comprehend, a slow-motion existence in an extreme environment. The secret to this incredible longevity isn't a magical fountain of youth, but something much more fundamental: cold. The near-freezing water, hovering around 1 to 2 degrees Celsius, dictates the pace of everything. This extreme cold forces the shark into a state of profoundly slow metabolism. Every chemical reaction in its body, from digesting a meal to repairing a cell, is dialed down to an incredibly slow rate. Think of it like putting life in a refrigerator. The processes of decay and aging, which are themselves biochemical reactions, are dramatically decelerated. Their heart beats just once every 10 to 12 seconds, a slow, deliberate rhythm pumping cold blood through a body built for patience. This slow pace of life extends to every aspect of their existence, including reproduction. A Greenland shark isn't considered sexually mature until it is around 150 years old. Imagine waiting a century and a half to reach adulthood. This strategy, while successful for a stable environment, makes the species incredibly vulnerable. The loss of a single adult female means the loss of centuries of growth and future reproductive potential. For these sharks, time is not a race. It is a vast, open ocean to be traversed with unhurried purpose, where generations are measured not in decades, but in centuries. Look closely at the eye of a Greenland shark, and you will likely see something strange. Dangling from the cornea is a parasitic copepod, Omatocoita elongata. Nearly every single adult Greenland shark is a host to these creatures, which latch onto their eyes and permanently damage their vision, often rendering them almost completely blind. But this parasite has a strange secret. It is bioluminescent. Why would a parasite on the eye of a deep-sea animal glow? One theory suggests the glowing lure might act as a fishing light, attracting curious prey like squid towards the shark's mouth. In this dark world, a debilitating parasite might have accidentally become a useful tool. So how does a nearly blind predator thrive in the abyss? It navigates a world of scent and electricity. Their sense of smell is extraordinarily acute, capable of detecting a carcass from miles away. The scent molecules travel slowly in the cold water, creating long, stable trails for the shark to follow. But even more impressive are its ampullae of Lorenzini, a network of pores on its snout filled with a conductive gel. These pores are so sensitive they can detect the faint bioelectric fields generated by the muscle contractions of living prey, even if it's completely hidden and motionless under the sand. The shark doesn't need to see its next meal. It can feel its heartbeat. For a long time, their age was a mystery. How do you determine the age of an animal that has no bones to form growth rings? The answer was found in the most unusual of places: Cold War nuclear bomb tests. In the 1950s and 60s, atmospheric testing released a massive pulse of carbon-14 into the global ecosystem. This bomb pulse was absorbed by all living things, creating a permanent timestamp in their tissues. Scientists discovered that the proteins in the center of the shark's eye lens are formed at birth and never replaced. By measuring the amount of carbon-14 in that core tissue, they could precisely date when the shark was born, using a nuclear signature to read a living creature's birth certificate. This immense lifespan raises questions about the very nature of aging. At a cellular level, aging is often linked to the shortening of telomeres, the protective caps on our chromosomes, and the accumulation of DNA damage. The Greenland shark must possess remarkably efficient DNA repair mechanisms and ways to mitigate oxidative stress over centuries. Their proteins also have to be incredibly stable to resist denaturation and degradation in the cellular environment for so long. It's a living laboratory for studying longevity, not through a single trick, but through a whole suite of adaptations, from slow metabolism to robust molecular machinery, all working in concert to defy time in the deep, cold dark.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.